Let us now move on to Unit 4, which is the application of the measurement of angles and its direction traverse surveys. So, as a general background, traversing or traverse surveys is a type of survey in which a number of connected survey lines from the framework and the direction and lengths of the survey lines are measured with the help of an angle measuring instrument and tape or chain, respectively. So bear this in mind that traversing contains of two main components, angles and distances. Next. Now we have the two types of traverse surveys. It is said to be an open traverse when the line from a circuit ends elsewhere except the starting point. This is suitable for surveying a long narrow strip of land as required for a road, canal, or the coastline. Next. Then the second type is a closed traverse. It is known as a closed traverse when the lines from a circuit at ends and starts at the same point. This is suitable for locating the boundaries of lakes, woods, and or a survey of large areas. Next. Now let's go to the methods of traversing. Next. So the first method is called chain traversing. It is done by taking linear measurements only, hence a chain or tape is enough for chain traversing. The angle between the adjacent traverse lines is measured using the chain angles concept. Chain traversing is performed in areas such as ponds where it is difficult to adopt triangulation. So the chain angle concept is about finding the angle between two adjacent sides by establishing the third side using tie station. This angle between the sides can also be fixed by establishing a chord of known length between the sides. So this one in the picture is called a surveying chain. Next. Then second method is compass traversing. In compass traversing, the magnetic bearings of the survey lines are measured by a compass and the lengths of the lines are measured either with a chain or with a tape. Both fore bearing and back bearing are measured and the required corrections for local attractions are applied. So the one in the picture is called survey compass. Next. So the third method is theodolite traversing. In the case of theodolite traversing, the linear measurements are done by using a chain or stadia method and angular measurements are done by the theodolite. Using the theodolite, the magnetic bearing of the first traverse line is measured and from that magnetic bearing of other sides are calculated. This method is very accurate compared to other methods. And the last one we have a plane table traversing. In the case of a plane table traversing, the measuring and plotting of the traverse on the paper are done simultaneously. The plane table equipment is set up at every traverse station one by one in a clockwise or anti-clockwise direction. The sides of each traverse station are drawn on paper to a suitable scale. If there is any closing error, graphical methods are used for its adjustment.
So now let's proceed to balancing and area computations for a close traverse. So by the way, I am Eves Joshua Kamay and I will be reporting about traverse computations. So traverse computations determines if the observed angles fulfill the geometric constraints of the figure. So the following are the computations and adjustments required for a closed traverse. So first, the latitudes and departures and their respective algebraic sums. Second, the calculating the total error of closure. Third, balancing the survey. Fourth, determining the adjusted position of each traverse station. And lastly, computing the area. So now let's proceed with the latitude and departure. So latitude of any line. So latitude is the projection on the north and south lines. Also, it can be called north or positive latitude and south or negative latitude. So the departure also is the projection on the east or west lines. And it can also be called west or negative departure and east or positive departure. So the closure of a traverse is checked by computing the latitudes and departures of its sides. So the departure and latitude are essentially the x and y components in a rectangular grid system. So x component is the departure. So here, so since the departure is from east to west, so it our departure is the x component. And since our latitude is north to south or south to north, so our latitude is in the y component. And for latitude, our formula will be L cosine alpha, for departure L sine alpha. So the alpha is the bearing angle and the L stands for the length of the line AB. So now let's proceed with the error of closure. So there is always an error in any closed traverse. For a closed traverse, the sum of the north and south latitudes must be always zero. Therefore, the summation of latitudes is equal to zero, and for departures as well is equal to zero. So error in latitudes or E sub L. So this means that it is the resulting error when the latitudes are added together. And for error in departure also, it is the resulting error when the departure are added together. So if the bearings and distances are plotted in a sheet of paper, the figure will not close because of error in departure and latitude. So as you can see here in the figure, we have an error in departure and in latitude. And for the error of closure, our formula will be uh, the square root of E sub L squared plus E sub D squared, or the error in latitude squared plus the error in departure squared. And for the precision as well is the error of closure over the perimeter. So now let's have an example which about which is about latitude and departure and error of closure. So we can see here in our figure below, we have a figure here which is a closed traverse. So now our formula for latitude is L cosine alpha, and for departure is L sine alpha. So first we need to get this line first. So in order to get this line, we need to find the departure. The departure is L sine alpha. So since it is west, so it is negative since it is going to the left. So therefore, uh, manipulating the formula and substituting the values, we will get negative 20.63 feet for the departure. And for the latitude, given the formula, then substitute again the values, and then we get negative 188.40 feet. So again, it is negative since it is going to the south. And for the second line, same process again for departure. Substitute the given, and now it is on the east, and it is going to the right. Therefore, it is positive. And our departure for BC will be 86.62 feet. And for latitude BC, since it is going to the south, it is negative, and the value will be negative 152.27 feet. So in this table, uh, we put all the values here, and as you can see in the side AB, we have negative 188.403, and for departure, we have negative 20.634. And this is for side BC. And solving for side CD, we will get these values for latitude and departures, and so on. And we need to sum up the length, the latitude, and the departure in order to get the error of closure. So for the error of closure, this will be the formula, and substituting the values, we will get 0.182 feet for the error of closure. And for our precision is we we put the values again, and we will get 1 over 5,176. So our for this example, our error of closure is 0.182 feet, and for our precision is 1 over 5,176. So now let's proceed in balancing a survey. So there are rules in balancing a survey. So first is the compass rule. So compass rule is the correction to be applied to the latitude or departure of any course is to the total correction in latitude or departure as the length of the course is to the length of the traverse. And the second rule is the transit rule, which is the correction to be applied to the latitude or departure of any course is to the total correction in latitude or departure as the latitude or departure of that course is to the arithmetical sum of all the latitudes or departure in the traverse without regards to sign. So the compass rule assumes that angles and distances have same error, and errors are accidental. So the compass rule states that the error in latitude or departure of a line is to the total error in latitude or departure as the length of the line is the perimeter of the traverse. So now let's proceed to an example of balancing a survey. So recalling the results of the previous example from the latitude and departure, so we have this table. We have this table again, and we need to remember this summation of the length, the latitude, and the departure, since these values will be used in the next slides. So again, we get this line, the latitude given the formula, we get the negative 188.40 feet, and this will be the formula in the correction in the latitude AB. So manipulating the formula, we will get this, and substituting the formula, we will eventually get 0.016 feet. So E sub L is this value here, 0.079 feet, and the L sub AB will be the 189.53 feet over the perimeter, which is the summation of all the length of all lines. And now let's proceed with the departure AB. So given the formula again, we will get negative 20.623 feet. And we have this correction formula and manipulating the formula and substituting the formula again. So we have in E sub D, we have 0.163 feet multiplied by the L sub AB, which will be 189.53 feet over the perimeter, which eventually equals to 0.033 feet. So we need to get the latitude and the departure corrections for each line and putting this in the table to sum up the results. So the value will be for the length 189.53 will be 0.016 and 0.033 in latitude and departure. And solving for the length 175.18, we will get the correction 0.015 and 0.030. And continuing the process, we will get these numbers. And also for this balance, we will get these values, and summing this up, the latitude and the departure, we will get zero values. This means that there is no error in corrected latitudes and departures. So that would be all for this example, and next reporter will be Christian Tautuan for the computations in area.
Hello everyone, good morning. So now it is my turn to report to you about the area computations for a closed traverse. So first are the methods of determining the area of a closed traverse. An important objective of most land surveys is the determination of the area of tracts of land. The most commonly used SI unit of area measurement in this case is hectare when large tracts of land are measured, while when smaller tracts like that of the subdivision lots, playground, small farms, cemeteries, and building sites are expressed in square meters. 1 hectare is equal to 10,000 square meters. Now, there are different methods used in determining area, and I will explain it to you individually. So here are the methods. This includes the use of triangles, the coordinate method, the DMD, and the DPD. So we will tackle about it. First, here's the area by triangle method. The triangle method is a useful and fairly accurate method of computing the area of traverses that have only few sides. This method is well suited for determining the area of small tracts of land and was popularly used before the engineer's transit was invented. Now, in using the triangle method, there are cases that are commonly used to determine the area. These are the triangles with known base and altitude, having two sides and inclined angle, and having a measurement of all three sides. First case is the known base and altitude. Now, from that figure, it can be said that the area of triangle whose base and altitude are known or measured may be computed by this formula, which is just simply the area of the triangle. Area is equal to 1/2 base times height, where the letter A is the area of the tract of land in square meters, B is the base or any side of the triangle, H is the altitude or the perpendicular distance from the corner opposite the base. So that's it for the known base and altitude. Now let's proceed to the two sides having included angle also. So When the lengths of two sides and the included angle of any triangle are known, its area is given by the formula area is equal to 1 half AB sine theta. So as you can see in the figure, the inclined angle alpha is um, is included at the sides of A and B. So the formula is applicable wherein A is the area of tract of land, the small letter case A and B represents the sides of the triangle, while the alpha is the angle between sides A and B. Next, the third one, or the third case, is the three sides measured. So this states that the area of a triangle whose three sides are known can be computed by the formula area is equal to the square root multiplied by S times the quantity of the difference of S and A times the quantity of the difference of S and B and times the quantity of the difference of S and C, where A represents the area of the tract of land, A, B, and C are the sides of the triangle, and the S in the formula represents 1 half of the perimeter, or just 1 half A plus B plus C. And so that's it for the three cases. Now, how to solve the total area using the triangle method? The area of any field in the shape of a geometric figure can be found by dividing it into a series of triangles. When the sides or diagonals are measured, the area of the triangles are computed separately. The area of the field is then taken as the sum of the areas of the triangles into which field is divided. With the formula A is equal to A sub 1 plus A sub 2 plus A sub 3 is the formula to get the total area of while using the triangle method, wherein A is the total area of the tract of land, A sub 1 represents the area of the first triangle, A sub 2 is the area of the second triangle, and A sub 3 represents the third triangle. Now, we'll have an example applying the triangle method. Here's the problem. A surveyor sets up a transit at P, which is located in the middle portion of a four-sided tract of land and reads directions and measures distances as given below to the five corners. Find the area of the tract in square meters. So what can you see at the right side of the screen is the table containing the given line, the given bearing, and the given distances. And here's the given. So first, let us calculate the angles about station P with this figure, having this figure based on the problem. So first, we'll get the angle of the triangle APB, the triangle at the top part of the traverse, which has a 41 degree 30 minute plus 38 degrees plus 10 minutes is equal to 79 degrees 40 minutes. Next is the angle of the triangle BPC, which can be simply obtained by deducting the sum of the given angles, the 38 degrees 10 minutes plus 70 degrees 20 minutes from the supplementary angle, which is equal to 180 degrees, which then turns out to be 71 degrees and 30 minutes. Now, let's get the angle of the triangle CPD. That's the triangle at the bottom part of the traverse. So we just simply add them. You just simply add the angles between them. So we'll have an angle of 130 degrees plus 35 minutes. Next is the angle of the triangle DPA, which is also calculated by deducting from 180. So we have angle at DPA, which is 78 degrees and 15 minutes. Next one is we'll calculate the area by using the case or the second case, which is having two sides and an included angle with the formula A is equal to 1/2 AB sine alpha. So first we'll get the area of the first triangle, which is the triangle APB. We'll have 1/2 AP times BP sine theta. I mean sine of the angle APB. So we'll input the given, and so we'll get the area of the triangle APB as 107,463.56 square meters. Next is the second triangle, which is the triangle BPC. So the same process as what we've done on the triangle APB. We'll input the side A, which is in this case is the BP, the side B, which is the CP, and then the alpha, which is the angle BPC, will have an area of the triangle BPC of 113,742 square meters. And that's the same process also in getting the area of the triangle CPD and area of the triangle DPA. Now, next is to determine now the total area using the formula total area is equal to A sub 1 plus A sub 2 plus A sub 3. Now, in this case is the total area is to be computed by adding the area of the triangle APB, the area of the triangle BPC, plus the area of the triangle CPD, and plus the area of triangle DPA, which have the values 107,463.56 plus 113,742 plus 100,000.12 plus 118,581.81, which will then get the total area of 440,787.49 square meters, or in hectares, 44.0787 hectares. So that's it for the triangle method. Let us now proceed to the second method, which is area computation using coordinates. The method of coordinates is another useful method for computing the area of any closed figure bounded by straight lines. The calculation involves determining the areas of the individual triangles or trapezoids formed by projecting lines upon coordinate axes. The coordinates used are the total latitudes y and the total departures x for the corners of the closed traverse. Now, shown is a figure of a closed traverse put in a quadrant and have the following coordinates reflected in the table. It is advantageous to have the traverse portrayed in one quadrant so that the coordinates of all points are positive in sign. And so what was seen in the table are the corners A, B, C, and D having their respective x and y coordinates, being total departure as the x coordinates and total latitude as the y coordinates of the closed traverse. And so based on that figure, it can be derived that the area of ABCD is equal to area of trapezoid AB plus area of trapezoid BC minus area of trapezoid AD minus area of trapezoid DC. Or it can be rewritten as area of ABCD is equal to 1/2 x sub 2 y sub 1 plus x sub 3 y sub 2 plus x sub 4 y sub 3 plus x sub 1 y sub 4 minus x sub 1 y sub 2 minus x sub 2 y sub 3 minus x sub 3 y sub 4 minus x sub 4 y sub 1, or just simply 1 half multiplied by the matrix of the x and y coordinates, being the x coordinates at the top row and the y coordinates at the bottom row. And now, for the general form to determine the area of a closed traverse having any number of sides is this formula: 1 half times the matrix of x and y coordinates with the nth number ending at x sub 1 and y sub 1. So why do we have to end it with x sub 1 and y sub 1? So in order to create a closed traverse, we need to start from the first point and end also at the first point. That is why we need to start the matrix at the x sub 1 and the y sub 1 and end also at x sub 1 and y sub 1 so that we can have a closed traverse. Now, we will have an example using the coordinate method. Now, given the following latitudes and departures of a closed traverse, determine the area of the traverse by the coordinate method. So here is the given table. Now, we'll need to use or to apply coordinate method using the formula 1 half x sub 2 y sub 1 plus x sub 3 y sub 2 plus x sub 4 y sub 3 plus x sub 1 y sub 4 minus x sub 1 y sub 2 minus x sub 2 y sub 3 minus x sub 3 y sub 4 minus x sub 4 y sub 1. And now we'll have to substitute all the given in the formula. So x sub 2 means the x value at the second station, which is 2085.03, multiplied by y sub 1, or the total latitude at station 1, which is 100, added to the product of x sub 3 and y sub 2, which means x sub 3, or the or the total departure at the third station, and y sub 2, the total latitude at the second station, plus so on and so on. So you'll just have to see the row and column of the table. And now we'll have the area of the closed traverse using the coordinate as, which is equal to 198,240.63 square feet, because this is in square feet. And so that's it for the coordinate method. Next one is the area computation using double meridian distance, or DMD. Now, area by double meridian distance, um, the meridian distance of a line is defined as the shortest distance from the midpoint of the line to the reference median. The double meridian distance of a line is the meridian distance of the line multiplied by 2, which is why double. Now, in this method, strict attention to signs is absolutely necessary in the computation of areas. The use of double meridian distance is to determine the area of a closed traverse. This method is an adaptation of the method of determining areas by coordinate method. It should always be remembered that before the DMD method can be applied properly, the latitudes and the departures of the traverse should first be adjusted such that the figure becomes a closed polygon. Now, the latitudes and departures of the traverse should be first adjusted. So that's what we need to remember. Now, there are rules to be considered in computing the DMD for each course of a traverse. Now, the first rule states that the DMD of the first course is the departure of the course itself. Second rule, the DMD of the succeeding course equals DMD of previous plus departure of previous plus departure of course itself. Rule 3 states that the DMD of the last course is the departure of the course itself, but opposite in sign. Now, don't worry because you'll know how to apply these rules later on. The traverse area is then computed using the DMD method, having the formula double area is equal to the DMD multiplied by the adjusted latitude. Or we can have area is equal to 1/2 times the summation of DMD times adjusted latitude, or just the summation of the double area. Or it can also be presented as the area multiplied is equal to 1/2 of the summation of NBA, or the north double area, or the plus areas, plus the summation of the south double areas, or the minus areas. Now, to appreciate the rules and the formula, we'll now have to apply it in an example. So here's the problem. Find the area of the closed traverse shown below using DMD method. So here are the given departure and latitude in its respective lines. So line AB has a departure of positive 2.29 and has a negative latitude of 20.55. Line BC has a departure of negative 57.91 and has a latitude of positive 11.26. Line CD has a departure of negative 3.47 and has a latitude of positive 19.7. Line DA has a departure of positive 15.09 and a latitude of negative 10.41. The first thing we need to do is to compute the DMDs. Now, in order to compute the DMDs, we need to refer to the rules in computing the DMD. So, just here, this is where the rules will be applied. So, listen carefully. So, the first DMD, or the DMD of the line AB, is just equal to its departure, as what was stated in the rule number 1, which states that the DMD of the first course is the departure of the course itself. So as you can see, the departure of line AB is positive 2.29. So its DMD also, it's 2.29. Second is the DMD of the line BC. So bear in mind that in the following lines of getting the DMD, you need to apply rule number 2, which states that the DMD of the succeeding course is equal to the DMD of previous. As what you can see here, the DMD of previous is 2.29 plus the departure of previous. The departure of previous is also 2.29 plus the departure of the course itself. So in this case, its departure is negative 57.91. And so add all them up, we have negative 53.33 as the DMD of the line BC. Next is the DMD of the line CD, which also applies rule number 2. So again, the DMD of CD is equal to the DMD of the previous, which is negative 53.33, that is the DMD of the line BC, plus the departure of previous, which is equal to negative 57.91, and plus the departure of the course itself, which has a value of negative 3.47. Now, add it all up, we have the DMD at line CD equals to negative 114.71. And for the last line, which is DA, it just simply states at the rule number 3 that the DMD of the last course is the departure of the course itself, but opposite in sign. So As what we can see in the table, the departure at the line DA is positive 59.09. And if we employ rule number 3, we just have to change its sign from positive to negative. And so we'll have the DMD of line DA. And now after computing all of the DMDs of each line, we now have to compute for the double areas, in which the formula is equal to DMD times the adjusted latitude. So the DMD is the one that we computed earlier, multiplied by its respective latitude. So first one is the double area at line AB, which is equal to 2.29, which is the DMD, multiplied by the negative 20.55, which is the latitude. And the double area of line AB is equal to negative 47.06. For the double area of line BC, we'll have negative 600.50. For the double area at line CD, we'll have negative 2259.79. And lastly, for the double area at the line DA, we'll have positive 615.13. And now, if we'll encode it in tabular form, we'll have this. So this is what it looks like. So we'll have lines, the departures, the latitudes, and the DMD and the double area of the respective lines. So next, now we'll have to compute the traverse area. By using the formula 1/2, the area 1/2 multiplied by the summation of the double area. And so first we'll need to add all of the double areas. So negative 47.06 plus negative 600.50 plus negative 2259.79 plus 615.13, which is equal to negative 222, negative 2292.22 multiplied by 1/2, we'll have negative 1146.11. And in this case, the negative sign is disregarded. And so we'll have the final area or the final answer of equal to 1146.11 square meters. That's it for the DMD. Now we'll proceed to the DPD or the double parallel distance. Now, in the double parallel distance of a line is equal to twice its parallel distance. By using the latitudes of the successive courses instead of departures, parallel distances can also be computed in a manner similar to meridian distances. In parallel distances of a line is the distance from the midpoint of the line to the reference parallel or the east-west line. In this method, also, signs must be put properly. And it is for this reason that the DPD method is often used as a check on area computations when the adjusted latitudes and departures are known or can be determined. So it is said that the area determined by the DPD method should equal to the area computed by the DMD method. DPD also has rules in order to have or to compute the DPD for each course of the traverse. And now, for the rules of DPD, we just have to simply change the DMD to DPD, and instead of using departures, we'll have to use the latitudes of the traverse. So here states number 1, the DPD of the first course is the latitude of the course itself. For the second rule, the DPD of the succeeding course equals to the DPD of previous plus the latitude of the previous plus the latitude of the course itself. And rule number 3 states that the DPD of the last course is the latitude of the course itself but opposite in sign. So It's similar in the double meridian distance. However, we'll use the latitude instead of the departure. And so the traverse area is then computed using the DMD method, which is the double area is equal to the DPD. Be careful now, we'll use DPD instead of DMD multiplied by the adjusted departure and um, not the latitude. And so area is equal to 1/2 multiplied by the summation of the double area, or can also be presented as area is equal to 1/2 multiplied by the summation of EDA or east double area plus the summation of WDA or the west double area. Now we'll have an example of employing DPD method. And so we'll have the same example as what we have on the DMD method, but now we'll use the DPD method. So we have the same given also. First, we'll compute for the DPD. So the same, we'll need to stick to the rules in computing the DPD. So in getting the DPD of line AB, we just have to is the course itself. So as what was stated at rule number 1, the DPD of the first course is the latitude of the course itself, which is in this case is equal to negative 20.55. Next is the DPD at line BC, which is equal to the DPD of the previous. So it is negative 20.55 plus the latitude of the previous, which is also negative 20.55 plus latitude of the course itself, which is equal to 11.26. And now we'll have the DPD at line BC is equal to negative 29.84. And for the DPD at line CD, we'll use the same rule, the rule number 2, and we'll have a positive 1.12 DPD. And lastly, for the DPD at line DA, we just have to change the sign of the latitude of um, the line DA. And so we'll have a positive 10.41 DPD. And so that's it for computing DPDs. Now, after computing DPDs, we'll use it in computing our double area. So first is the double area of line AB, which is equal to negative 20.55 times the departure 2.29, which is equal to negative 47.06. So the same formula also for the succeeding double areas. So double area at line BC is equal to positive 1728.03. DA at CD is equal to negative 3.89, and the DA at line DA is equal to 615.13. Now in a tabular form, here's what it looks like. And now we'll have to compute for the area. And in computing the area, we'll use the formula area is equal to 1/2 multiplied to the summation of DPD times the adjusted departure, or just simply the summation of the double area. So we'll have to add all the double area. So negative 47.06 plus 1728.03 plus negative 3.89 plus 615.13, which is equal to 2292.21, and divided by 2, we'll have the area of 1146.11 square meters. Now, remember the one that I said that the area computed using the DPD method must be equal to the computed area using the DMD method. Now, As you can see, the area using BPD will have 1,146.11 square meters, and we'll check again the computed area at DMD using DMD method. So it was 1,146.11 square meters. So they are equal. So that satisfies the rule that it needs to be equal. And so that's all for today. That's all for the Unit 3 and Unit 4. Thank you so much for listening. Now we're open to questions. Thank you.